Hi guys, this lesson is on 4.6 Trigonometric Graphs. So first thing to cover is a bunch of terminology. So a trig graph, also called a sinusoidal function, is a periodic function. So that means that it keeps repeating. So they look like waves, and if you know anything about what a wave looks like, it's identical over and over and over again. That's what we mean by periodic function. The period is how long it takes to complete one full wave. So one full top of the wave and one full bottom of the wave. Sinusoidal functions, these are these wavy functions that I'm going to show you. Sine or cosine is what we study. The median is the middle of the graph, so you can draw a line, a horizontal line down the middle, and it should cut the graph into a top wave and a bottom wave. And then the amplitude is how far from that middle line that you draw to the very top of the wave or the bottom. Here is the sine function. So this, if you put in your graph in your calculator, y equals sine x, and you set your window to be what I'm showing here. So the y-axis is going from -1 to 1, and the x-axis is going from -360 to 360. And you put your calculator in degree mode because the x-axis is degrees, then you should get a wavy sinusoidal function that looks like this. Now, a few things to notice. The line down the middle is actually the x-axis on this function. This is your median. Okay, the equation for your median here would be y equals 0, or the x-axis. If you look at that red line, it cuts this whole function into a top wave and a bottom wave, and the size, or like the height there, which we call the amplitude of the wave, would be the same for the top one and the bottom one. That's how we know it's cutting down the middle. Now, up here in green, you can see I've shown you what a period is. That's how long it takes for one complete wave. So if I was to trace from the very top to the very top, and then I was just going to move it over, kind of like this red thing I have here, if I just move this over, if it was drawn perfectly, it creates, if I move it all the way over like that, it creates the next wave cycle. So I can literally just pick up one period of the wave and copy and paste it over and over and over again, and it will show me this picture, this periodic function that I'm drawing. Now we've got a maximum shown up here. We've got the amplitude shown, and you can see that at any top part of the graph or any bottom part. The amplitude is going to be the same in any of those max or min locations. We've got a minimum down here. We've got the period shown just in a different spot. If I go from the middle here like this, and I do one full up and one full down, I've got right back to where I would do one full up and one full down again. So once I trace out one bit of the pattern, and that would just keep repeating over and over and over again, I've got one period. So it doesn't necessarily have to be from a maximum to a maximum or a minimum to a minimum. It can be from one point of the graph to the identical point later on down the graph. So amplitude of this mother function, remember we talked about transformations in the first unit, we're going to talk about them again, is 1. So if you graph a basic sine function, it's going to have an amplitude of 1. Then we're going to do a bunch of stretches and reflections and things and see how that changes. Your mother function has a period of 360 degrees. All of these could be translated into radians. We can work with radians as well. And the median is at y equals 0. So you can imagine if I start doing transformations and moving this up and down, maybe my median would move with my graph. Here's the cosine function. The big difference here is where it starts. So we've still got a period that's 360 degrees. And on this picture, I've just done it in radians, but 2 pi is the same. We've got an amplitude of 1. The median is still at y equals 0. But if you compare it to the sine graph over here started at the origin. The cosine graph starts at a value of 1. And I'm going to show you with a little animation why that is. So up here actually is a good picture to show you the difference between sine and cosine. They're the exact same wave, just starting at different positions. So if I trace the sine wave like this, and I just move it over, I literally get the cosine wave. So they are the exact same picture, they're just located in different spots on the Cartesian plane. This comes from the unit circle. So let me show you an animation that does a pretty good job of kind of showing you why this happens. Okay, so this has a lot going on. I'm just going to look at the sine graph right now. You can see that as we go around the unit circle, if we were to look at the sine value, so the second coordinate of the ordered pairs, they go from being 0 at the start to 1 at 90 degrees, back to 0 at 180 degrees, to -1 at 270 degrees, and back to 0 once you do a full circle around the unit circle. So what this is showing you is it's showing you as your angle gets bigger, the sine value down here is changing, and they're just graphing it based on that. So I think that this animation really helps you to see what's happening. If I put cosine on here, you can see that the cosine values, remember, they're the other point on the unit circle, they're the first x coordinate. They are all the same numbers, but they just occur at different times. So where you might start at 0 for sine, you start at a 1 for cosine. So this website is mathwarehouse.com. I just Googled sinusoidal animations, and this can really help you to understand why when we're going around a circle and we start graphing it on a Cartesian plane, does it end up in this wavy form. The tan graph you do not need to know. We're going to skip over that. And this is very, very important. So pause the video and get all of this written out so that you can just listen. This is a snippet from your formula sheet. This is combining transformations that we did in Unit 1 with specifically sinusoidal graphs. It's all the same transformations, but it's done within a sine or a cosine graph. So up here, I'm showing you what we've already learned with all of our transformations. We've seen that, we've used it before. We're just literally in this unit, instead of saying it can be any function, we're saying it's either a sine function or a cosine function. That's the only difference. And when we're talking about sinusoidal functions, we give things like the vertical stretch, horizontal stretch, different specific names. So here we go. The A value, whether it was in Unit 1 or now, is still called a vertical stretch. But on the picture, since it corresponds to this wavy picture, we now know that sinusoidal graphs have an amplitude. That's exactly what the vertical stretch is going to tell you, amplitude. Your B, it was tricky. Back in transformations, it's tricky again. There's some memorization that needs to happen here. It is still a horizontal stretch of 1 over b. Remember that you needed to flip it. That's why it was tricky. But this is absolutely important for graphs. The b value is related to the period in this way. So if you have the b value, whether you're in radians or degrees, you're going to choose one of these. If you sub the b value in there and go 2 pi divided by b, you're going to get what your period is of your graph. So you can't just look at B and say, oh, the period of the graph is 2 because B is 2. It's not that simple. You have to put it into your formula, divide it, and then say, oh, the period is pi because 2 pi divided by a B value of 2, the 2's cancel, my period is pi. So you have to do a little more work with the B value always. The C value is just how far you move horizontally. That's not different. Horizontal translation, we just call it a phase shift in sinusoidal functions. The other thing, remember, is that it's the opposite direction of the sign. So if it's a minus C, it actually goes right C, and if it's plus, it goes left. And your D is your vertical translation, which also gives you your median. Okay, because that mother function, sine theta, cos theta, those have a median at 0. So if you move that whole graph up or down, your median also goes up or down. So once you know your D, you know your median right away. Couple other calculations that can be really useful are the max and the min. If you go from your median and you add your amplitude, you're going to get to the maximum. If you go from the middle line and you minus your amplitude, you're going to get to the minimum. Let's take a look at all of this stuff on some examples. So I've started off just by drawing the mother function. So y equals sine x. Remember, it goes from 1 to -1. One full period here would be 360 degrees. And then you could divide this off. Half of that would be 180. Quarter of that would be 90, and so on and so forth. We really are looking at the shape, more or less. I do recommend that you have a good working graph, whether you print off some graph paper and you sketch one really accurately, or you just copy one from the internet and know how to reproduce it. A good working copy of the mother function will help you in this section. Now, they want us to graph y equals 2 sine x. So we look at that, that's an A value. A value is vertical stretch. How did we perform vertical stretches back in Unit 1? First thing we said is that if we were stretching it vertically, all of these x-intercepts were invariant points. Then we said a point like 1, if I stretch it vertically and I multiply it by 2, it ends up here at 2. -1 would end up down here at -2. So all my y values get doubled. If I then connect those as best I can, and it doesn't look pretty, but there you have it, I see that my sine function has now been vertically stretched by a factor of 2. So let's take a look at all of the characteristics that we can figure out now. Vertical stretch of 2 about the x-axis. That was our proper terminology. That's what we would have said in Unit 1. We can still say it in this unit, but in this unit we can be more specific and we can say that that means the amplitude is 2. From the midline right here to the very top of the red function is 2 units. So the max, the min, the median, the range, and the period are all things that we can find here. Let's start with the median. Now the median of the mother function is at 0. We said invariant points were on the x-axis, so the median is also invariant. The other thing that you can see up in the equation is that there could be a +0 at the end. That's the D value in the equation. That's the median, so it's at 0. Now the maximum is going to be the median all the way up for how much the amplitude is. So if I go from 0 and I go up 2, I'm going to get a maximum at 2. If I take my median and I minus my amplitude, I've got a minimum down here at -2. Up here, we've got 2. That kind of looks confusing. Now let's talk about the range. Let's write it in this notation with the square brackets because it's easiest for these. What's the very bottom point of this graph? -2. What's the very top? 2. What are those two numbers coming from for the range? The minimum and the maximum. Once you have those, you have the range. Now the period. Let me trace it out so you can see it. If I start, let's say I start at the origin. That's the easiest place most of the time to measure the period. I need to do one full up and one full down, and I end up right here, 360 degrees. If I was asking you for this in radians, it'd be 2 pi. So that's one full wave on the graph. You can do it from max to max, but think about how you're going to do that. You're going to have to do some kind of subtraction with those two numbers. Much more complicated than just starting at 0 and doing one full wave. Okay, let's do this one. Now we've got a negative in there. So think back to our first unit. What would we say? We would say that this is a vertical stretch of 3 about the x-axis, and we would say it was a vertical reflection. So it's going to be exactly like the last one where we stretch it, but then we're also going to reflect it. So where this point here would have gone up to 3, now it's being reflected down to -3. Okay, so that would happen with all of these points. They get reflected and multiplied by 3. If I connect them, and this is not the best picture, you can see my invariant points more or less on the x-axis still. I get this picture. So this is -3 sine x. What is my amplitude? It's the same as my vertical stretch. It's 3. Amplitude is a measure of how high the waves get. Don't use the negative. Amplitude is just a positive number. What is the median? If my invariant points were still always on the x-axis and the x-axis was my median to start with, it's still, there could be a 0 at the end, it's still y equals 0. My max. I take my median plus my amplitude, I get 3. My min, median minus amplitude, -3. Range, from the smallest number to the biggest, square brackets, period. Nothing changed about my period here, so 360 degrees or 2 pi. Next example, here's a little snippet of what it would look like on your calculator if you tried to graph this. Keep in mind, if you're trying to put this in your calculator, you need to change your window. Because if you have a window that goes 10 to 10, you aren't going to see very much of the x-axis because the x-axis goes from -360 degrees on this picture to 360. So if it only goes to 10, you're barely seeing any of this. Okay. Here's the mother function, cosine x. The reason why I know it's cosine is because it's starting up here at 1. What have they done with this mother function? Well, they've said +2 at the end, not attached to the x. So if it's not attached to the x, that means it happens to the y values. The y values have all gone up 2. That's how we got that graph. So let's talk first terminology. This is a vertical translation 2 up. What did that change? Not only did the graph move up, but the original median also moved up too. So where would the median be now? If it was at 0 before, now it's at 2. Remember, the median is the d value, the value that you add on the end there. Now, in order to get max and min, I need to be able to take my median and add my amplitude or minus it. So I'm going to have to figure out what my amplitude is here. I took the mother function, I picked it up, and I moved it up 2. Did I do anything to stretch it? No. If I'm not stretching it, my amplitude up here is the same as it was down here. So you need to be able to tell me what's the amplitude of the mother function. You should have that memorized. The amplitude of the mother function is 1, then the amplitude of this is 1 because we didn't stretch it vertically. That's when the amplitude's going to change. The other thing that you can do is the amplitude, the A value, is always sitting in front of the sine or cos. So if nothing's written, it's a secret 1. That's where you can find the amplitude. Okay, so let's do max then. Midline plus amplitude, our max is at 3. Midline minus amplitude, our min is at 1. If I look at the picture, that makes perfect sense. I can then say that this graph goes from the smallest value being 1, the biggest number being 3 for range, and period, nothing has changed. It still takes 360 degrees or 2 pi to complete one full wave. If you think you're getting the hang of this, you can pause the video now and try and do this vertical translation down. It's still a cosine mother function right here with a midline at the x-axis, and they want you to move that whole shebang down 2. This is going to be a vertical translation to down. The amplitude I can see right there in the equation is 1 because I didn't stretch anything. Then I'm going to say my median is my D value. And you'll notice I'm always writing my median as an equation. It's the line y equals -2. It's not just a floating -2. That means nothing. It's that entire line through the graph. My max is going to be from my median, adding my amplitude. It's okay that it's still negative. My min is from my median minusing my amplitude. My range, now which number is smaller here, -1 or -3? Look on the graph if you can't tell. What's smaller, -1 or -3? -3 is smaller than -1. You can't write those backwards. And again, we haven't changed anything with the length of the wave, so the period is still 360 or 2 pi. Here we go with a phase shift or a horizontal translation, both of which you can use to describe this. Horizontal translation is what we would have said in Unit 1. Phase shift is more specific to sinusoidal graphs only. This is going 90 degrees, and remember it's the opposite of the sine. So you would think that would mean left, but it actually means right. Okay, this is called phase shift. So let me trace it out. This is the mother function. Just kidding. This is the mother function. Sine x, remember, starts on the origin. That's how I knew it wasn't the mother function. What they've sketched for you there is they've sketched the transformed function. They've moved my red graph 90 degrees, which is this far. Refer back to your first graph you drew if you're not sure. They've moved it that far. That's how they got this picture. So here's your sine x. Here's your sine x minus 90. So if you were to graph this in your calculator, the mode is very important. That has a degree sign on it, so you're only going to see this in your calculator if you put it in degree mode. Now, a few things have not changed here. The range, which comes from the max and the min. I just took that graph, I shifted it left and right. Nothing has changed about the maximum and the minimum of that graph. Nothing's been stretched vertically. The period, is not changing at all here. It's still going to be 360 degrees. Or if this had a pi in it, I would say 2 pi instead. Okay, here's the one that's a little bit more tricky. We've got a b value. Now, when you've got a b value like that, it's telling you something has happened to the period, but it's not telling you exactly what happened. You must memorize this. Okay, this is the radian version. This is the degree version. Now, what's happening here is that our period is, let's just do this in radians because we haven't, and usually this is what we would work with, is 2 pi divided by b. Our b is 2. The 2's are going to cancel. My period is pi, or 180 degrees. So this is my original function. My original function is here. That's cosine. Because see, it takes 360 degrees to do a full wave. What happens when the b value is 2 is you've done a horizontal stretch of 1/2. Remember, you flip it from the first unit. So what's happened is all of this horizontally has been squished so that it happens faster. This wave happens to have more cycles faster than the green one. Okay, so where it took 360 degrees before to do one period, now we've got a wave happening from here to here in 180 degrees. We just so happened to do it in radians, so it went from 2 pi to pi, but that's exactly what's happening. You've got your waves happening faster. You have more waves on the same domain that you can see on your screen. Now you could still figure out that the amplitude is 1, the max is 1, the min is -1, the range. You could figure all of that out using the same strategies. Here we have the questions. Page 233, 4 to 11, 13, and 15a. The other thing I'd like to assign is that you sketch yourself some mother functions. Give yourself a very high quality, detailed sketch of sine x and cosine x. You can use your calculator. You can use videos online to help you sketch it. You can rewind the video, pause it, and sketch the one that I have. But essentially all you're doing is you're plotting all the points from your unit circle. You're figuring out the sine values from your unit circle. You're plotting them on a Cartesian plane. You can use that website that has the animations also to help you, but give yourself a really accurate picture that you can use throughout this entire section on graphing. Let me know if you have any questions.